So we looked at the relationship between rate of reaction and concentration. We see that the rate of the reaction changes with concentration. And so if we use an integrated rate law, and that is calculus, taking the rate law and literally integrating it, which we won't get into, we can look at the relationship between concentration and time, which is much more useful and practical. The integrated rate law depends on the order of the reaction. So again, looking at a very simple reaction with one reactant going to products. We're going to look at the first order law first, because it's first, right? So the rate is equal to a rate constant times the concentration. So we can go through all of this business and we get the differential rate law. That's all very nice, but I don't care about that. This is what we're really interested in, is the integrated rate law. So the natural log of the concentration at some time t is equal to negative rate constant times that time t plus the natural log of the concentration at time 0, the starting concentration. So when we graph this, so this is an equation in the form of a line. Your y equals mx plus b is the equation for a line. So here's b, the natural log of a0. X is time, y is natural log of t, and the slope is negative k. The rate constant is positive, but the slope is negative. And it's just calculus. We're going to say, we believe you, okay? So we can use graphing to analyze reaction data, and we will be doing that. We're going to all learn how to use Excel and find out how very wonderful it can be. But let's look at this decomposition reaction. They're monitoring the concentration of the reactant at a fixed temperature as a function of time. And so here we see the different times that it was sampled, all the way up to 1,500 seconds, and these are the concentrations. We are supposed to show that the reaction is first order and determine the rate constant. So we could try to do things by, calculating average rates at various times and try to do something like that. But now that we know about the integrated rate law, we don't need to do that. We'll take the data and graph it. So we'll graph the natural log of the concentration as a function of time. And we get a nice straight line because this is, made up data. And here's the equation that Excel can give us, where this is the slope and this is the intercept. So the rate constant is equal to what? The negative slope. Rate constant equals negative slope. So the rate constant is 0.000290. How are we demonstrating that this is first order? Because this particular graph gives us a straight line that tells us it's first order. If we do this graph with 0 or second order, it won't be a straight line. Okay? What are the units on the rate constant? We can't really pull them out of the equation, but what's the rate law for a first order reaction? Yeah, it will be, because the rate needs to be molarity per second, and because this is molarity, then this must be 1 over second. So the unit here, s to the minus 1. Okay? Any questions? Here is the answer written in scientific notation. Yes?
So if our graph's different, we can't use the integrated rate law?
If you do the natural log of concentration versus time and you don't get a straight line, then you need to try a different order. Yeah. Because you could, out of a curve, it'll fit a line to it and give you a slope, but it's not going to mean anything. Yes?
So what are we putting into Excel? What are we putting into Excel?
That's a great question. So let's look at that.
Oh.
So what we would do in Excel, and this is where Excel is wonderful because you don't have to do all of these calculations by hand. So we have the time. We want the natural log of this. So we're going to take the natural log of this and have Excel do the calculation for us. And then we're going to copy that all the way down the column, and it's going to do the natural log of all of those things, and then we graph natural log versus time. Okay? It's just so much easier when you don't have to repeat everything. Any other questions? So this question is saying, use the graph and best fitting line to predict the concentration at 1900 seconds. So the equation for the line here, y equals negative 0.000290 t minus 2.3. Y is the natural log of SO2 Cl2. Slope and the intercept is the natural log. Well, let's see, this is the concentration at time t. And this is the natural log of the concentration at 0. Okay. So we know what that number is now. It's negative 2.3. At 2.30, actually. So if we want to know this concentration at a particular time, we're going to take the time and put it in here. Oh, that's supposed to be an equal sign. I'm just going to call this A because that's too long. Oh, I know what I did wrong there. There was an equals and a negative sign. Times the 1900 minus 2.30. Now, a lot of people can take it written like this and solve it on their calculator. But you also might need to just do all the math on the right side and write that down. So if I can get this to turn on. I actually remembered to look for my good calculator. Could I find it? Either one of them? Or my husband's? No. So I'm dealing with this one, but it'll be okay. Okay, so I'm getting negative 2.851. Anybody confirm that? Yes, you got two. Okay, perfect. Okay, so logarithms are something that don't show up in everyday life, right? And so it's super easy to forget how they work. But it's very important to remember or relearn how they work because they're not going away this semester. So natural log is a function like multiplication or division is. It's not a variable, so you can't divide by natural log. You have to do the anti-log. The anti-log of natural log is e to the x. So what we'll do is we'll take e to the x of both sides. So e to that equals e to the negative 2.851. Here we have log and anti-log canceling each other out. So the concentration that we're looking for is e to the negative 2.851. And your calculator should have a button for that. And I don't think mine does. Okay, so what is e to the minus 2.851? 0.057? And there was some more?
786.
786. Okay. Sig figs and logarithms, just kind of weird, especially with natural log. But for logs, it's really the decimal places that are the sig figs. So here, I would consider this number to have 3 sig figs, and I'd want to keep 3 here. If you're not sure, keep 1 or 2 extras. That never hurts anything, okay? You can always chop them off at the end. Any questions? Now, you should have a calculator with a solver. If you have the TI-36X Pro, it has a solver on it. And what you can do with a solver is you can take a big equation like this and put X in for this concentration, and you can let your calculator do all of the algebra. It's a beautiful thing, okay? That's not cheating, it's using a tool, okay? So if you want help learning how to make your calculator do the algebra that you don't like, I'll do my best to show you. I'm good at the TI-36X Pro, not so good at the rest of them. So 5.78 times 10 to the minus 2. Cyclopropane rearranges to form propene. In the gas phase, the reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 to the minus 5 per second at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235 minutes? Okay, so there's a lot of words in there, and there's a fair number of numbers too. One of the important things to pick out is first order, okay? It's first order. So then we know what the integrated rate law is. Natural log of A at time t equals negative rate constant times the time plus the natural log of A at time 0. And we will often use A instead of cyclopropane because there's no benefit to writing out the formula over and over and over again. So that's what first order means. Here we're given the rate constant. Well, let's write that down. K equals 3.36 times 10 to the minus 5 per second. We're given the temperature. Do we need the temperature? No, we don't. Why are they throwing that in there? Well, kind of to trick you, but also because the rate constant is temperature dependent. So anytime you say the rate constant is this, you really should say what temperature it is. So the temperature's in there. It's all cute and nice and everything, and we're not going to use it. So here we've got the initial concentration is this. So that's going to be A at time 0. And we're asked what the concentration will be after 235 minutes. can we take these numbers and put them into the equation? Not yet. Because the rate constant is in seconds. So whatever time they give you, you have to convert it to seconds. So we'll multiply by 60 seconds per minute. This calculator does multiply, thankfully. 235 times 60. $14,100 seconds. So what we're trying to find is that guy right there. Yes? So we will put all this other stuff in. Negative 3.36 times 10 to the minus 5 times 14100 seconds plus natural log of 0.0445. Okay, yeah. I started it. My calculator doesn't do standard. Okay, what's the result there? Doesn't do the log for me. 0.0277? Oh, you already solved for it. Okay. So that's the final answer, is the concentration. Just for completeness, what's the natural log? Anybody?
Negative 3.58602,609.
So e to this number gives us 0.0277 molar. Is that a reasonable concentration? Like, how am I supposed to know? Well, the initial concentration is 0.0445 of the reactant. The reactant concentration gets smaller. So it could be wrong still, but it's reasonable because it's less than the original concentration. Any questions? And there's the answer. I started putting the answers from the back of the book up here because sometimes I do them wrong. And the students didn't always catch me. And then I feel really kind of stupid later. Okay, that was first order. Second order. The rate law for second order, rate is K times the square of the concentration. Or we can express that, well, and then the rate is this. And so that's just going through the math and getting to the good part. This is the integrated rate law. So this one has fractions in it. So here we have for our y equals mx plus b. So y here is 1 over the concentration at the time t. X is time, again, that's here. The slope now is the same as k, and the intercept is 1 over the initial concentration. This is a common technique that scientists use. It's not as critical now that we have computers that can do all kinds of fitting of lines and curves and things. But in the olden days, we had graph paper. And I never used a slide rule, but they did use slide rules to do the logarithms. And they wrote down all the logarithms or whatever, and they graphed it on a piece of paper. And you drew the line that looked the best to you. And if you could figure out how to graph the data So it gave you a straight line. You could get a lot more information than trying to look at a curve and it's like, what's the rate constant from this curve? Really hard. But you make it into the form of a straight line, and now we can just pick out the rate constant. Eesh. So again, with the graphical analysis, you're decomposing NO2. Function is monitored at a fixed temperature. The concentration at a fixed temperature is a function of time. The data is tabulated, show by graphical analysis that the reaction is not first order and that it is second order. Determine the rate constant. So how do we show that it's not first order?
They are.
We make a first order graph, natural log of the concentration versus time. If it's not a straight line, it's not first order. To show that it is second order, we'll do a second order plot, 1 over the concentration versus time. Then we expect a straight line. So here is the first order plot. And, if you're not looking too carefully, you might say, well, that's not so bad. But at the beginning, the points are above. In the middle, the points are below. Come on, pointer. Great. And at the end, the points are above. We have mystery green hand stuck on the screen. Let's see. Over here is the second order graph. And here we see that the lines are fitting, the points are fitting very nicely on the line. Now, obviously, if you have real reaction data, especially from a Chem 1B student lab experiment, your data is not going to be this beautiful. How can you tell if it's not a straight line or it's just kind of rough data? Well, if it is a straight line and it's just not very beautiful, you should have some points above and some points below scattered all over the place. You shouldn't see a trend like this, where it's above, below, and back up again, because that's a curve, not a line. What is the rate constant? It's the slope, right? It's this guy right here, 0.255. How would we figure out what the units on that are? We would look at the second order rate law. This is supposed to be molarity per second. This is molarity squared. So then this needs to be 1 over molarity times second. Okay. I don't remember the units for the various rate constants. I just figure them out when I need them. Use the graph and best fitting line to predict the concentration of NO2 at 2,000 seconds. Now, what we don't want to do is we don't want to look at this and say, oh, well, we'll just look at the graph and figure it out. For one thing, it's way off the end, right? For another thing, reading stuff off the graph is not very accurate or precise. Really precise is probably the more important problem. We want to use the equation, okay? So for the second order, okay, what? There we go. 1 over the concentration is the rate constant times time, plus 1 over at 0. So our rate constant, we're just using the line here, 0.255 and we determined that that was per molarity per second, times 2,000 seconds, plus 100, and that unit there would be 1 over molarity. This is equal to 1 over A. So 1 over A .255 times 2,000 plus 100 equals 610, and the unit would be 1 over molarity. How do we find out what A of t is? Here we have the reciprocal. We want to upside down this. We want to take the reciprocal of this to get A of t. So we're going to take the reciprocal of the other side. 1 over 610. So 1 divided by 610. No, there's just... too many sig figs, but it'd probably be about 3. Any questions? What was the initial concentration of this compound? 1 over the initial concentration was 100. So 0.01. So A0, oops, did that wrong. A0 is 1 over 100, or 0.01. This number is smaller than that number, so that's encouraging. Doesn't prove anything, but it's encouraging. Any questions? I think that when I use A instead of NO2 or some long chemical formula, it makes the whole equation just a little easier to look at, right? Because you stick all that other stuff in there, and it was just visually disturbing. It looks so complicated, when it really isn't. And the 0 order integrated rate law. 0 order rate equals the rate constant times the concentration of the 0 power, which is just K. And so you go through the calculus and you end up with this. The concentration at time t is equal to negative rate constant times t plus the original concentration. The plot of the concentration versus time is linear. Here's our y. It's the concentration. Mx plus b. We're just graphing concentration versus time. So, whoops, come in, go backwards there. Now it went back to, okay. So those are the integrated rate laws. Anybody have any questions? It kind of seems like a lot of stuff, but you just need those 3 equations, right? And I mean, they won't give them to you on the final, but they probably won't ask you about them. I'll probably give those to you on a regular exam, because I sometimes have a hard time remembering them. They're easy to get mixed up. Like this one has a negative K, and first order has a positive K. No, second order has positive K, first order is negative K, right? It's just like, which one is it, right? So the important thing is to be able to use them. The pattern is the same. They are in the form of a line. Okay, let's talk about half-lives. A half-life, symbolizes T1 half, is the time needed for the concentration of the reactant to fall to 1/2 of its initial value. So half-life, the time for half of it to go away. So if the initial concentration is 0.5 molar and T1 half is 50 seconds, what will the concentration be after 50 seconds? It'll be 1/2, right? It'll be 1/2 of the original concentration. So 0.25 molar. After 100 seconds, it'll be half again. Okay? The half-life expression is going to be different for different reaction orders. What we did here works with a first order reaction, but it's not going to work with 0 or second order reactions. So how do we get an equation for T1 half? So this is a rearrangement of natural log of A at T equals negative KT plus natural log of A, 0. We can take this and rearrange it. It involves knowing how log functions work, and we could talk about that in lab. We're not going to get into it now. So looking at this, when T is equal to T1 half, we know that AT equals half of A0. So we can plug that in. So up here for AT, I'm going to plug in 1/2 of A0. The denominator is A0, and that is equal to negative K times T1 half. So inside this term, the A0's cancel out, right? So that is equal to log of 0.5, or 1/2. I can't remember exactly where I was supposed to go with this, but what's the natural log of 0.5? I think it's 0.693? Negative 0.693. So I've got negative K T1 half equals negative 0.693. Multiply both sides by -1 to get rid of the minus signs. Divide by K to get T1 half by itself. T1 half for first order is equal to 0.693 over the rate constant. Any questions? Yes?
Why is it dependent on initial concentration?
That's a good question, because it's a first order reaction. A zero order reaction is not dependent. Oh, I'm sorry. You said, why is it not? Yeah. Well, I was thinking incorrectly, but I gave the correct answer. Because it's a first order reaction. So first order reactions have the same half-life regardless of how much you start with. Their half-life doesn't change. Nuclear decay is a first order reaction. And so you can look at the half-life of plutonium something or other. It doesn't matter how much you start with, the half-life is always the same. And it's just a function of the first order. It's a good question. Anybody else? So, as you noticed, half-life is independent of the initial concentration for first-order reactions. So here is what we were looking at last week, the concentration versus time. We see that this is a curve, right? So if we start with 1 molar, after 1 half-life, we're down to 0.5. After 2 half-lives, we're down to 0.25. 3 half-lives, 0.125. And you just keep going. You move over what's equal to a half-life, and you cut the concentration in half. Images here depict a first-order reaction at various times. The black circles represent reactant A. Red circles represent B. What is the half-life of the reaction? What does half-life mean? The concentration has been cut in half. This is our initial concentration. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 dots per square. That's the concentration. So we're looking for 5, right? That's more than 5. 1, 2, 3, 4. Close, that's 6. This one. Now we're down to 5. The initial concentration has been cut in half. So the half-life is 90 seconds. Questions? Another first-order reaction, the half-life is 25 minutes. If the initial concentration is 0.3 molar, what is the concentration after 50 minutes? Do not use the calculator. Okay, so this is the Chem 3A method of doing half-lives. There's an equation, and we could figure it out, but we're not going to. It starts with 0.300 molar. After 1 half-life, it's going to be 0.150, right? How much is a half-life? 25 minutes, right? So if we do another half-life, another 25 minutes, now we're going to get 0.0750 molar. So total elapsed time, 50 minutes, and that's what it asked for. What did I do wrong?
Yeah.
It's asking for the concentration of B. Thank you. See, didn't read the question very good. So I found the concentration of A, didn't I? I'd like to say I did that on purpose. I didn't. I screwed up. It's a good lesson, though. So if this is the concentration of A now, how do we know what the concentration of B is? All of the A that was lost became B, right? So the initial concentration minus the current concentration this is how much we started with. This is how much is left. This is how much A was destroyed. That is equal to how much B was formed. And that's also an example of why sometimes multiple choice questions are helpful. Because I came up with an answer that wasn't a choice, and that immediately told me I did something wrong. Except on my exams, when I give you multiple choice questions, I know the common mistakes students make, and I put those answers on there. So, any questions? First order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant to fall to 1/8 of its value? Well, again, we're not going to do any fancy math here. We're starting with original value 1. After 1 half-life, it goes to 1/2. And then it goes to 1/4. And then it goes to 1/8. Right? How many half-lives was that? 3 half-lives. 3 times 26.4 seconds. $79.2. So some half-life problems involve some fairly serious math. Others involve cutting things in half and counting how many times you did it. Yeah. So, don't overthink things. Don't make things harder than they need to be. Okay, what about second order? So here we have the second order integrated rate law. And again, we're going to find the equation for T1/2 by realizing that A at time T1/2 is going to be half of the original concentration. So we're going to have 1 over 1/2 A0. Okay, that looks dangerous, so I'm going to fix that up right now. That is the same as 2 divided by A0. That is equal to KT plus 1 over A0. This is T1/2. So to solve for T1/2, I need to get rid of this. This is what I want to keep. Stuff that's added or subtracted, you get rid of that first, and then you can divide by stuff. So I'm going to take this and subtract it from both sides. So I'm going to get 2 over A0 minus 1 over A0. What does that equal? 1 over A0. Right? So that is equal to 1 over A0, and that is equal to the rate constant times T1/2. Divide both sides by K. T1/2 is equal to 1 over K times the initial concentration. Any questions? I will warn you that there will be some problems, and I think we'll see an example, where it'll ask, well, how long does it take for it to get to 90%? Or 73.6% or something ridiculous like that. And you're going to use this same concept, except it's not going to be this nice 1/2. But you'll plug things into the integrated rate law and solve. So the half-life does depend on the initial concentration. If you have a low initial concentration, you have a longer half-life. So as the reaction proceeds, the half-life gets longer and longer and longer. For the 0 order, same strategy here. AT equals 1/2 A0. That's not a very nice one. I want to get the KT by itself. I'm going to subtract A0 from both sides. And I think about that, and it's like, that's going to get a little messy. I'm going to end up with negatives on both sides. So I hope this isn't skipping too many steps. I'm going to add kt to both sides, and I'm going to subtract this from both sides. And a0 minus 1/2 a0 is equal to 1/2 a0. So, oops, forgot the half there. T1/2 is equal to the initial concentration divided by 2 times the rate constant. Half-life is also dependent on the initial concentration, but the half-life gets shorter as the initial concentration gets smaller. So the half-life gets shorter and shorter and shorter as the reaction proceeds. The slide is advancing on my iPad and not on the computer. There we go. Table 15.2, rate law summary table. Super useful, okay? You might want to take a screenshot of it so you can look at it whenever you want to, right? This has all the stuff we talked about. So it's got rate laws for the 3 orders, the units, integrated rate laws, what will give you a straight line plot, and the half-life expressions. So a decomposition reaction has a rate that is observed to slow down as the reaction proceeds. And it has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true for this reaction? Plot of the natural log of the concentration of the reactant as a function of time is linear. Half-life increases as initial concentration increases. Doubling the initial concentration quadruples the rate. Okay, those 3 choices are all really different, right? They're not just changing a word or something. It's not like, oh, it's 0 order, it's first order, it's second order. These are kind of crazy things. So instead of trying to pick those, let's look at the question and see, what do we think the order of the reaction is? Because we have enough information to figure it out. The half-life depends on the concentration. That tells me it is not first order. First order doesn't depend on it. So it has to be 0 order or second order. The rate slows down as the reaction proceeds. 0 order or second order? Second order. Okay, so now we know this is a second order reaction. If we plot natural log of A versus time for second order, will it be linear? That's first order, so that's not going to work. The half-life of the reaction increases, as the initial concentration increases. And I'm thinking, I have to think too hard about that one. Let's look at the last one. A doubling of the initial concentration results in a quadrupling of the rate. Is that true for second order? Yes. So I know that this is true. So a really good guess is that this relates to the 0 order. C. Any questions?